Section 3.3, we're looking at a new type of function, a logarithmic function, and we're also going to talk about what their graphs look like. And it just so happens that logarithmic function is actually the inverse function of exponential functions. Okay, so we already have a good idea of what an exponential function looks like, and to figure out what the graph of a logarithmic function looks like, we just simply need to mirror it about y equal x as we would with any inverse function. Okay, and it's this section where we learn how to solve exponential and logarithmic functions, and we use the fact that they are inverses of each other. So we start out with the definition of a logarithmic function. Again, it says let a be positive. We do not want a to equal 1, just the same conditions as we had for the exponential functions. Then for x greater than 0, logarithm base a of x is defined as the following. Okay, so here is an exponential function. Okay, this is the form of equation that we saw in the previous section. So if x is calculated by taking an a and raising it to a power of y, then we can write the inverse function, or the logarithmic form of this equation, by simply recognizing a as the base of the exponent. So if a is the base of the exponent, then you would write the log function with a subscript indicating the base of the log function, and it would be the same base. So if a is the base of the exponent, then a is going to be the base of your log. Okay, then the log base a, we take the opposite side of the equation, the x, and it will be what's called the argument of the log. Alright, and I always like to say the log equals the exponent. Okay, it's a phrase that I've memorized, and so it comes in handy when I want to convert from an exponential form of an equation to a logarithmic form of an equation. So I know what the base is going to be. It's going to be a, because the base of the exponent's a, and then I say the log equals the exponent. So on one side of the equation you have the log, and then on the other side of the equation you put the exponent, which was y, and then that only really leaves one place to put the x, and that is once again as the argument of the log. So in example 1, what we're going to be doing is switching, well, maybe not example 1. Example 1, well, yeah, we'll switch over to the exponential form of the equation, which will make it easier to calculate these log functions. So in example 1a, we have log base 2 of 16. Of course, you could put this into your calculator, or you could rewrite it in the exponential form, where we said the base of the exponent is the base of the log, and so it works the opposite way. The base of the log 2 would be our base of the exponent. We don't know what the exponent is. It's a question mark. The log equals the exponent. So what do we raise 2 to get 16? Well, it turns out we raise 2 to the 4th to get 16. So log base 2 of 16 would equal 4. as I mentioned before, you can also put this into your calculator, and if you have one of the newer model TI-84s, then to do that you would simply go to Math, and as you notice on your keys, you probably notice that there's a log button, but this log button is specifically for a base of 10. Okay, then you have an LN, which is specifically for the base of E. So we want a log base 2. So what we need to do is go to the Math menu and select log base, hit enter, and then we can type in our own base. In this case it's 2, and then our argument of the log is 16, and we hit enter, and we get the same result as we did with the exponential form of the equation. We get 4. Some calculators don't work exactly the same way, so we're going to teach you a different way to calculate this with the change of base formula in a following section. Okay, but with this example we really want to focus on switching over to the exponential form of the equation. So once again we have log base 5 625. The base of the log is 5. Log equals the exponent, so we don't know what the exponent of this 5 should be, but whatever that exponent is gives us 625. Okay, if you play around with your calculator and you raise 5 to the, let's say, 4th power, we would get 625. So in other words, 5 to the 4th equals 625, and so log base 5 of 625 should be equal to 4. If you have, like I said, the newer edition calculator log base, it just simply makes it easier by showing or being able to type the numbers into a subscript. Some calculators don't do it that way, but in our case our subscript would be 5 and the argument would be 625, and if we hit enter now, our calculator returns the value of 4. Alright, log base 10, and we do have a log base 10 button on our calculator, and with 10 being the base, if we convert to the exponential form of the equation and log equals the exponent, we don't know it, I'll put a question mark. What number do we raise 10 to get 1 over 100? Well, to get 100, first we would need to raise 10 to the 2nd power, and then to get the 100 on the bottom of the fraction, we would need a negative in our exponent. So if I take 10 and raise it to the negative 2, that would become 1 over 10 to the positive 2, which is 1 over 10 times 10, 100. So log base 10 of 1/100th should give us a negative 2. If we hit log of 0.01, which is 100th, and hit enter, we get negative 2 from our calculator. Or you could hit log 1 over 100. You get the same result. And then if you go to Math, log base, type 10 as your base, and then 1 over 100 as your argument, negative 2 once again. So any of those will do the trick. If log base A 243 equals 5, then what does A equal? Okay, once again, A is the base of our log, and so A would be the base of our exponent. So in other words, the log equals the exponent. And so now we don't know what the base is, but we raise this number to the 5th power to get 243. At this point, we want to get rid of the 5th power, and so what we could do is take the 5th root of both sides, and then okay, the 5th root cancels out the 5th power, and so we have A equals the 5th root of 243, which gives us something that we can type into our calculator. You don't have a 5th root button, and so from intermediate algebra you would have to remember that the 5th root radical can be expressed as a fractional exponent 1/5. So we can raise 243 to the 5th power instead of using a 5th root radical. And so I type parentheses 243, and then on the outside of the parentheses I raise it to the power of 1 divided by 5, enter, and I see that that number is 3. So A equals 3, answering our question here. 3. If you have forgotten this trick of switching from a radical expression to an exponential expression, then most calculators have, let's see, a radical button, or you can go to the math menu and you can select the radical with the variable as the root number, enter. And so here we have a spot where we can enter in a number. I have A and S there, but we would enter in the number 5 for the 5th root, and then inside the radical 243, and that would give us the same result, 3. So continuing with the examples, C, it says log base A of 0.343 equals 3. Then what does A equal? Alright, the base of our log is the base of our exponent, and log equals the exponent, so I have an A to the 3rd power, and that tells me that when I raise that number to the 3rd power, I get 0.343. Well, how do we undo this power of 3 to get our A by itself? Well, we simply take the cube root of each side. So we want to calculate the cube root of 0.343. To do that, we call up our calculator again, and we do have a cube root selection under the math menu, so I'll call that one into the home screen, and I'll type in 0.343 and hit enter, and we see that that number is 0.7. So A equals 0.7. Okay. We could verify that with the calculator, going back to our math menu, selecting log base, typing in a 0.7 for the base, and then the 0.343 for the argument, and when we hit enter, we get the exponent again. We get 3, which is what we started with on the right hand side of the equation, 3. F, log base 2 of x minus 1 equals 3. What does x equal? Alright, so the base of our log is the base of the exponent. Log equals the exponent, and so 3 is our exponent. So 2 to the third would equal the argument of our log, which is x minus 1. So what is 2 to the third power? Well, that is 8. So we have x minus 1 equals 8. If I add 1 to both sides, that will give me x equals 9. And that was the question. What does x equal? Well, it equals 9. So from this section, you definitely need to nail down the transition from a log format of an equation to an exponential and vice versa. So the bottom of the page mentions some special cases. 2 special cases for a equal 10 and a equal e. The first one is called the common log, and that pops up here on your calculator. This button, okay, log, and as I mentioned before, that is a log with a base of 10, but when you hit the button, the 10 isn't written in the calculator. It's just understood to have a base of 10. So what do we raise 10 to get 10? 1. 10 to the first power is 10. Okay, so common log, base 10. And then we have the natural logarithm, ln, for n for natural. It is a log. It is the equivalent of writing log with a base of e. Alright, but you'll probably never see it written that way. So ln of x is the inverse equation of x equal e to the y. Alright, y equal log x is in a sense the logarithmic format of this exponential equation. Okay, example 2 says use your calculator to approximate. And it says approximate because a lot of the times we use log to calculate something. We get an endless string of digits which we have to round at some point. So we end up chopping some of the numbers off. So we say estimate. Log 29. Real quick calculation because we have the log button. And so we just type in 29 for the argument and we hit enter. And so if we approximate that, we could say 1.46. Log of 3/4. We just simply type in log with a 3 divided by 4 and hit enter. We get negative 0.12, and I'll round it to the nearest thousandths, 0.125. And so this is approximate because I'm rounding. Then we have ln of 37. And so I hit the LN button. That's the great thing about the common and the natural log. We don't have to go hunting for the log base formula in the math menu. We type in 37 for the argument and we hit enter. And if I round it, I could write 3.61. And finally, we have log of 28.76. 0.76, enter. And if I round it, 1.459. Example 3 reads, convert the exponential forms to logarithmic forms and vice versa. So if we get an exponential, we go to log. If we get a log form, then we convert to exponential. Okay, so here we have t minus 1, and then we have a base raised to an exponent. So we want to convert to log form. Here, same situation, we have something with an exponent, 3 to the 4th. This will be converted to the log form. And here, obviously, we have log base 4, and then for D, we have the natural log with a base of E. So we will go to exponential form for C and D. Okay, so what we do is we have, for the exponential form, what we have is the argument equals the base of the exponent, and then we have the exponent. And so when we switch over to the log form, we write log with the base as the superscript or the subscript. Then we have the argument, and that equals the exponent. Alright, so we want to put things in their proper places. And so the base that we started with was A, the base of the exponent. And then we actually have the exponent, which is an expression x squared plus 3. Log equals the exponent. And then the argument is on the opposite side. And so the only other place left to put the t minus 1 is inside the log in the place of the argument. So we would write t minus 1 inside the log function. And I would put parentheses around it. So here we are, the log form of this exponential form. Again, over here, 3 is our base, and so we write log with a subscript 3. The exponent goes on the opposite side, and the exponent's 4. Log equals the exponent, opposite side of the equation, and the 81 would become the argument. C, here we have the exponential form up above of an equation, and the argument is here, x plus 5, so we start on the left writing the x plus 5. Then on the opposite side, the right side, we write the base, which the base of the log is 4, so the base of the exponent would be 4. And then the log equals the exponent. So what we have is a 4 raised to the square root of y minus c. So it's really just a matter of learning the proper places to rearrange the different parts. the argument, the base, and the exponent. And you need to go back and forth between the two forms. And so this square root of y minus c, this whole thing is a superscript. It's an exponent. D, this is the log form of the equation. We want to go to the exponential. Log equals the exponent. So on one side we will have, let's see. Okay, if we look back over here, we have the argument equals the base to the exponent. So I want to follow the same procedure. The argument of the log here is f. So I'll put it on the left since it's the argument. On the right side we have the base, and so what's the base of ln? You just have to know that. It's not written there. It's the natural exponential function, e. And so we've written the base e, we've used the argument f on the left, and the log equals the exponent, so we write x plus 5 as an exponent for the e. So this is our exponential form that we were looking for. Example 4, we're given f of x, log base 3 of x, and then g of x is log base 5 of x. And so we want to calculate f of 81, which could be written as log with a base 3, and then 81 is the argument. So what do we raise 3 to get 81? Okay, we want to know what this equals. You could type it into your calculator, but if you're familiar with the numbers and you know how to convert it to the exponential form, you could write 3 to what exponent equals 81. What do we raise 3 to get 81? Well, that would be a 4. 2 2's would give us 9, and we need 2 9's, so we need 4 3's. So f of 81 equals 4. Equals 4. Because 3 to the 4th power is 81. G of 1 over 125 would be log with a base of 5, 1 over 125. If we rewrite this in exponential form, we have 5. We don't know what the exponent is. Log equals the exponent. That's what we're trying to calculate. So we don't know what to raise the 5 to yet. So 5 to some number equals 1 over 125. Well, if I raise 5 to the 3rd power, I get the 125, but it's not in the denominator. So to cause 125 to go to the denominator, I would raise it to a negative number. I would raise 5 to a negative number. So what we do here is we say 5 to the negative 3 equals 125. And the great thing about this is you can do it several ways. If you're familiar with the different roots and raising numbers to the different powers, and you're familiar with the negative exponents, then you could probably come up with this like I did on your own. But keep in mind, anything you come up with, you can double check it with your calculator. If I raise 5 to the negative 3 power, well, I get a decimal, but it's real simple to take that decimal and convert it to a fraction. Go to the math menu and select fraction, and 0.008 is 1 over 125. If you didn't have a lot of time, then you could simply take log base 5 of 1 over 125 and go to the math menu and select the log base function and just type in your base and your argument 1 over 125 and hit enter, and we get the same result, -3. But again, if you're familiar with the numbers, sometimes it can save you a little time. If we do the same thing with A, log base, and here we had a 3, log base 3 for F, and then 81 returns the value 4, which is what we had. Example 5 reads, use a calculator to evaluate the functions f of x equal log of x, the common log, so this is understood to be a base 10. It's not necessary to write it. G of x equals ln of x at each value of 13, 17 over 28, and 32.86. So we take f of x and we plug in 13. That would be log of 13. The other number that we want to calculate as the input, 17 over 28, inserted into our function f would be log of 17 over 28, a common log. And then f of 32.86 would equal log of 32.86. So with the buttons on our calculator, this can be done fairly quickly. Log of 13, enter. Log of 17 divided by 28, enter. And then log of 32.86, enter. So f of 13 would give me 1.11 if I round it to the nearest hundredths. F of 17 over 28 gives me a negative result. I'll round it to 0.22. And then f of 32.86 yields 1.52. Now we want to do the same thing for G, which has a different base, still a log function but a different base. It's the natural log. So if I go through here and I replace our label in the function notation with G, then I need to go over here and put ln for our log function, and what's going to happen is we get different values. So I'll remove these three numbers that we got from our calculator, and now I'll simply just go back and hit the ln button for the same three numbers: ln of 13, ln of 17 divided by 28, and then ln of 32.86. Enter. So obviously we can enter in just about any type of number into these log functions: a whole number, a fraction, a decimal number. We can get back positive numbers, and we can get back negative numbers. So ln of 13, if I round to the hundredths, 2.56. ln of 17 over 28 is a negative point, let's see, 499. and then ln of 32.863.49. And that completes example 5, so we'll move on to the next page. Alright, so this remark is simply pointing out that these two functions are inverses of one another. With that being said, we are given an exponential function on the left in example 6, and so we want to write the inverse of each of these. Alright, in the previous section talking about inverses, that was back, let's see, I think that was section 1.6. What we would do is take the y and the x of the equation and swap them, and then solve for y, and that would give us our inverse function. And so in this case, in order to do that, we'll have to know how to convert an exponential into a log form. So if we swap our x and y, we would have x equals 2 to the y power. So in this case, for our inverse function of this exponential one, we would write 2 as our base, and so we would have a log base 2, and then the argument of the log would be the x, and the y from the exponent is taken care of with the f inverse notation. So very important to point out, the y is taken care of with this function notation here. Log equals the exponent, and the exponent was y. Alright, so with that being said, pretty quick to fill out the rest of these inverse functions. We're going to write log. The base of the exponent's 1.75, and then with f of x on the left, that would have been swapped out with an x instead of a y, and the 1.75 would have been raised to the y power. And so for our argument, we would use x as we did in the previous example. And as before, the y is replaced with the inverse function notation. So as it's written, this is a y equals 10 to the x. To create the inverse function, we go and we swap the x and y, like so, and so now we have an x equal 10 to the y, and if we solve for y, we have to do that with a log. We use the same base, 10, and the log equals the exponent, and so the y is replaced with the inverse function notation. Y, the log equals the exponent, and so this is used instead, the inverse function notation. And then the x is used as the argument of our log. Alright, on the right side of example 6, we start with the log and we want to go to the exponential form. And when we do that, we will have the inverse function, as long as we've swapped the x and y variables of this original equation first. So the way it's written, we have y equals log base 4 x. We swap the x and y, swap, and that gives us this equation. And to extract the y out of this log function, we need to convert this log equation to the exponential form. So over here, the base of the log is going to become the base of our exponent, and then the log equals the exponent, so the x just simply is written as a superscript for our 4. And once again, the y, which is the argument of the log, goes here and is written as the inverse function notation. So following the same procedure, converting this, or swapping the x and y, would give us x equals ln of y. The base of the ln is e, and we'll use it as the base of our exponent. Log equals the exponent, and so x would take the place of the superscript for e. For f, we have x equals, and I'm already swapping out x and y so that we can create our inverse function. And so what's the base of the common log? It is a 10. So the base of the log becomes the base of the exponent, and then the log equals the exponent, so x is going to take the place of the superscript above the 10. So you could write this as y equals 10 to the x. This is y equals e to the x. This is y equal 4 to the x. But these equations here are the inverses of these logs on the left. And so instead of writing y, we write f inverse with the -1 superscript. So now that we know the logarithmic functions are the inverses of the exponential functions, figuring out what their graphs look like is pretty straightforward. Any two functions that are inverses of each other are symmetric about the line y equal x. And so all we have to do is draw this diagonal line on our graph and then mirror the function to the opposite side. Okay, so here we have an exponential function, a to the x, okay, and this one's increasing, and so a must be greater than, let's say, 1 if we go from left to right and the function increases. Then when we mirror this across this diagonal is the equation y equals x. We get the inverse of the exponential. Okay, so the equation for this exponential curve here is y equals a to the x. If we do like we did in the previous example and swap the variables and then solve for y, we get log base a of x equals y, which is exactly what we have written there, log base a of x. And so these two curves are symmetric about this diagonal line y equal x. And so here with log with the same base a being greater than 1, the log also increases. So for either one, if a is greater than 1, they increase. It's just that the log increases at a much slower rate than the exponential function. Alright, over here we have the situation where a is less than 1 but still greater than 0. And so we see that our exponential decreases from left to right. And then if we take this exponential form of the equation and we convert it into the inverse, we would get log base ax. And so that you can see you can see that these are mirror images of each other. So let me just pick a few points to refresh your memory as far as what happens with the coordinates. Say for instance, okay, we have this point 0, 1. It's located right here. This is a point on the exponential curve. Well, when you take the inverse of that function, then as we did with the equation, we swap the x and the y, and the same thing happens with the coordinates. And so swapping the coordinates takes us to 1, 0, which is now a point on the inverse function, the log. Okay. Now let's say I pick a point, I'll pick this one, and we're going to sort of have to estimate. Here we have the coordinates 4 for y, and then I'll say this is about 1.6 for x. Then to get the inverse coordinates, we would write 4 comma 1.6. If we check that, then we go to x equal 4 and we go down and we get this point. And if we track our way over to the y coordinate or the y-axis, we get once again a y value of approximately 1.6. Alright, so for the coordinates on inverse functions, you just swap the x and y coordinate, and then you can graph the inverse. Page 84, we have a list of some properties of logarithmic functions. Since the log function is the inverse of the exponential, then you can see that we've sort of swapped the domain and ranges. For an exponential function, the domain was all real numbers, and then the range, it never crossed the x-axis, so it was from 0 to infinity. Well, with the inverse function, the range is now all real numbers for log, and then the domain just simply copied the range of the exponential, so the domain for the log is from 0 to infinity. Okay. 3, the point 1, 0 is its x-intercept. And if we strictly follow this format of the log equation, okay, no numbers in front multiplying the log, just a log with a base and an argument x, then we'll always get the x-intercept as 1, 0. Alright, the y-axis, with the exponential function, you remember that we never cross the x-axis. Well, with the inverse, that gets flipped, and now for the log function, it doesn't cross the y-axis, and so we call the y-axis a vertical isotope for the log function. 5, The function is 1 to 1, okay, just as the exponential function was 1 to 1. If the functions weren't 1 to 1, then you couldn't find the inverses of them. Okay, comment or property 6 here. The function log base ax is increasing for a greater than 1 and decreasing for a less than 1 greater than 0. Example 7. Use the following graphs to sketch log base ax for a equal 2, 1/3, and ln of x. Okay, base e basically. So here we have an exponential with a base of 2, and so what we're going to do is we're going to graph here on the far left log with a base 2 and an argument x. So what we'll do is we'll graph our mirror axis, and this is y equal x 6, and then we have 6, so the input equals the output. -2, -2, -4, -4, and we just draw a straight line through these points as best we can. I'm sort of getting off track there. But all we have to do is take these points that are plotted for the exponential form and reverse the coordinates. So let's pick one of these out. I'll say this is 2 and 1. Okay, it falls almost right in between 0 and 2. So these coordinates are 1 and 2 actually. And so I can swap those to get my inverse coordinates for log base 2x, and I would get the coordinates 2, 1. X equals 2, I go down to the y-axis 1, and there's a point. I just swapped my x and y coordinates. Let's see, if I go over and find the coordinates for this point at the far, at the very top, I could write 6 for y, and then that is about, let's see, I'm going to say 2.4. So to get the inverse coordinate, I just go here and switch them around. Y becomes the x coordinate, and 2.4 becomes the y coordinate. And so at 6 I go up 2, and then 2.4 is around about there. Okay, so I'll rewrite these coordinates up here. And now I'll pick one way over here. Let's say I pick x equal -2. And then what do I get for y? Well, I get just about one tick mark here. So I'll say 0.2. Let me see. Well, each 2 is divided up into how many? 1, 2, 3, 4, 5. Actually, this would be 0.4. Okay, so to get the corresponding coordinates on my inverse function, I swap them, and I say 0.4 and -2. And so I would go over one tick mark, and then I would go down to -2, and there is my corresponding point to this original point on the exponential. and they pretty much look like they're mirrored with respect to y equal x. And if you'll notice, the x-axis has a slightly different scale than the y-axis. Okay, y-axis only goes up to 6. The x-axis goes up to 8. So these don't exactly look perfectly mirrored. Okay, and I just noticed that I graphed these coordinates wrong. Okay, instead of graphing 2 comma 1, I graphed 2 comma negative 1. So this point here is obviously in the wrong place. And if we were to connect the dots, we would get a straight line here, which doesn't really mirror this curve of the exponential function. So I'm going to erase that one and put it in the proper spot right there. Okay, so always keep in mind that these points should look somewhat mirrored. At this point, I've got 3 points for my log function. All I have to do, since the exponential function is really close here by the x-axis, when I mirror that, the line for my log function will be really close to the y-axis. So I'll start out just barely scraping by the y-axis, and then I'll cut up through my first point, and I'll head over. Oh, that's not very good. Let me see if I can do a better job of that. Make sure I veer over and cross through my second point. Oh. And then curve up through this point over here, my last one. Alright, so that completes my curve for my log function. Alright, and they pretty much look like they're mirrored. Again, it's not going to be perfect because the scales for the x and the y-axis are different. Okay, this next one's going to be a little tricky. Again, I'll try to pick 3 different points along the original curve. Let's see, I will pick this point, and the coordinates look like they're about x equals -1 and y equals 3. I will go back and graph my mirror line. Okay, y equals x, and I simply just have to match the coordinates on the x-axis with the same number on the y-axis. So 4, 4. 6 would match up with 6 on the x-axis. -2 would match up with -2, x and y, and -4 would match up with -4. And now I connect the dots, giving me a nice mirror line to work with. Just sort of a way to double check yourself in the end. Might catch a mistake, as I did in the previous problem. And one point which is good to use in this case is this point, which pretty much falls on the line of symmetry. Alright, if you have a point on a curve that falls on the line of symmetry, then that point will not change for the corresponding inverse function. So I don't even need to know the coordinates of that point. It's going to be the same for the inverse function. And so now I'll simply go here and I'll pick this point, which I'm going to write as 2 comma, and that is really small. It's really close to the x-axis. I'll write 0.1. So for my inverse function, I'll simply swap the coordinates. Inverse function will share this one, and I'll write it in green. And so the inverse function will be 0.1, which will be really close to the y-axis, and then I'll simply go up 2, and these coordinates will translate to 3, -1. So if I go out 3 on my x-axis for my inverse function, and then I go down a -1, I'll have a green point that falls right about there, and those are matching up with these coordinates, +3, -1. And now this point, 0.1, which is going to be very close to the y-axis, I just simply skim along the y-axis and I go up to a +2, which would be right about there. I've got 3 dots now, and I just simply connect them. So if I start down here, which corresponds to this part of the exponential curve, I come in, I cross through this point on the y equals x line of symmetry, and then I shoot up through the third point, and then I get really close to the y-axis. Let me see if I can draw that a little bit better. There we go. That looks a little better. Doesn't line up all that great, but here is our, let's see, this would be log of 1/3, log base 1/3 x. It is the inverse of 1/3 to the x power. Alright, the base was less than 1, and so for the exponential it was decreasing. And then as well for the log, okay, log with a base that's less than 1, you can see from left to right it decreases also. It actually drops down in the y, the negative y region. And here we go with our last one, e to the x. I'll go ahead and sketch our y equals x line of symmetry. And I'll sort of approximate this one. Oh man. I want to go through the origin. Alright, there we go. Here's our line of symmetry. Y equal x. So I want to transfer these points perpendicularly through my axis of symmetry by the same distance. So I would offset by about this much perpendicular on the opposite side of y equal x. So I'd get a point somewhere in there. This point would transfer over here. And you can really only do this more accurately if the y and x axis have the same scales, but I'm just sort of eyeballing this. And now if I go to -4, that is approximately x equal -4 and y equals 0, so that would correspond to an inverse coordinate of 0, -4. which is right about there. So just real quick, just making sure these points are symmetric about y equal x. I've got 3 points now, and I'm just simply going to draw my log curve up through there and then swooping out to the side. And this would be the graph of log with a base of e x, okay, because this was e to the x, and log base e is ln of x. Like I said before, you'll probably never see it written this way. So this green curve represents ln of x, which is the inverse of e to the x. Exercise 2 just simply wants us to get some practice graphing these logarithmic functions with our calculator. So as before, when we wanted to graph something, we go to our y editor and we will graph log base x parentheses enter, and I'll put this one in green, graph. We'll go to zoom standard, and so here we go. This is our green curve, common log. What does ln of x look like? Ln x, close parentheses, enter. I'll put it in red. It shoots up slightly above the common log function. And what do we have here? Next we want to plot log 3x plus 8. And so the argument contains not only a variable but some numbers. Enter, graph. And now we can see if we plot g of x in blue, we can see that by adding numbers and multiplying the variable inside the argument, we've shifted our graph of the log function. Okay, the common log has shifted over by a certain amount, and maybe some other things have happened. Okay, what we'll do at this point is we will clear our y editor of the first two, and we'll take a closer look as far as what happened with our original log function whenever we multiplied x by 3 and added 8. We will zoom in So zooming in on our two functions we have graphed here, log, just the plain common log x is shown here, and then log of 3x plus 8 is shown here. And so, as before, whenever we add a number inside of the function, inside the argument to the x, we shift to the left. And so we've added a number, and so we shifted the common log to the left. Okay, same thing happens with the logs as they did for the other functions when we were talking about the transformations. We've also multiplied the x by 3, and usually that has the effect of squeezing the function, sort of compressing it or stretching it out. And you can see it has a slightly flatter shape than our common log function did over here on the right. Okay, we'll compare the natural log, ln of x, with ln of x, or 3x plus 8. Enter. Graph. And we see a similar situation here. Up above, we have the graph of ln in blue of 3x plus 8. So likewise, adding 8 inside the argument of the function has shifted it left. There was a transformation. So adding 8 shifted left 8. And then multiplying by 3 sort of compressed the original ln function. Okay, you can see once again this new function has somewhat of a flatter shape to it. Looks like somebody stepped on the top of it. Okay, and then what do we have? Our last function, h. I will put it, let's see, I'll put it in red. Green was our, well, let's see. No, I want to put this in green. Having trouble managing my colors here. I'll put this in green. ln of x will be in red. And so once again, here is ln of x. Here is ln of 3x plus 8. What happens if we make the ln negative and then have a plus 3 on the outside? So we have 3 subtract ln of a 4x, so it's probably going to be even flatter, but then we don't shift it left, we shift it right. 2 units. Graph. Okay, and once again this is in the green. Right there. Okay, so what's happened? Well, we have a negative in front of the ln now, and so that's mirrored it with respect to the x-axis. It's flipped it with respect to the x, and then we have taken this original ln function and went to the right. That came from the minus 2. Okay. If we could see more of it, you would probably see that this is flatter than ln of x. And you also see that it's moved up. Okay. So a lot of things happen between the base function and the final h of x. Okay. So this was just to really get an idea of the different things that can happen to the log functions and what their graphs look like and how to graph them on your calculator. Really nothing new here. Page 85, we've listed some properties of logarithms, and again, a is positive, a cannot equal 1. First, it says that log of a with the argument of 1, log base a1 equals 0, which makes sense if you write it in the exponential form. 1 in exponential form would be a to the 0 equals 1. Anything raised to the 0 power equals 1, and so log base a1 equals 0. It doesn't matter what the base is. If you raise it to the 0 power, you get a 1. 2, log base a of a equals 1. Again, writing it in the exponential form, we see that a to the first power equals a. Okay, we learned that in intro algebra, so this property makes sense. 3, log base a of a to the x equals x. So if we take a, the base, and that becomes the base of the exponent, we raise it to the exponent of x, then we get the argument of the log a to the x. So a to the x equals a to the x. Once again, makes perfect sense if you convert the log form of the equation to the exponential. 4, a to the power, here we have an exponential sort of mixed with the log, a to the power of log base a argument x equals x. Okay, so if we write a log, the base of the exponent here, so the fourth one, the base is a, so we write log a, and then we have, let's see, the log equals the exponent. So on the opposite side of the equation, we write the log that is shown as the superscript here. So log base ax goes on the right side of the equation, log equals the exponent, and then the opposite side of the exponential equation becomes the argument. So x gets replaced inside the log. And rearranging things that way makes perfect sense. Log base ax equals log base ax. And then 5, log base ax equals log base ay. Then x must equal y, and this just comes from the fact that the log function is 1 to 1. So 5, 1, 2, 1. Alright, example 8. Log of 4, log base 4 of 1. Doesn't matter what the base is. If the argument's 1, then we get 0. Okay, property 1. Alright, if the base matches the argument, that is property 2, which says that the result is 1. C, 10, to the log of 2x minus 1 over x plus 2. Okay, what does that equal? Well, you have to recognize that the base of this log equals the base of the exponent. Okay, and that aligns with, let's see here, property 4. And so if the base of the exponent equals the base of the log in the superscript, then we just write the argument of the log, 2x minus 1 over x plus 2. Well, that looks like we have a z there. It's really small, so you can hardly tell. Z plus 2. Property 4. D, ln of e of all of this stuff jumbled together as the exponent. So you need to see this as the exponent. Alright, well, this falls in line with property 3, which says if we have the log with the same base as the base of the exponent that's in front of it, so here the argument e is the same as the argument of the log, or the base of the log. Okay, you could see this as being written with a log base e and then e as the argument. Then you just simply drop the a's in the case of property 3, or in this case what we have is e. We drop the e's and we simply pick up the exponent of the e, and so what we would write on the right hand side of the equation is x to the 2/5 y to the 4th over z. Okay, the exponent that was shown here would simply be the end result. Ln is the inverse of e, and so these two pretty much cancel each other out, and the exponent drops down to the base level. Example 9, use property 5 above to solve each equation for x. Property 5 just says if you have two logs equal to one another and their bases are the same, then the arguments, since the log function is 1 to 1, then the arguments must be equal. So 10 minus 2x has to equal 3x. These have to be the same number. So we add 2x to both sides. 10 equals 5x, divide by 5. We get x equals 2. Okay. Same situation in B. Log base 4 on the left, log base 4 on the right. And so if these two expressions are equal, then the arguments must be equal. So this just becomes the equation x squared minus 6 equal 10. Add 6 to both sides. X squared equals 16. Take the square root and then pick up the plus or minus in front of the square root, opposite of the x. And so we get x equals plus or minus square root of 16 is 4. And that completes that equation. Okay, we are done. We solved it. Alright, bottom of the page, variations of logarithmic functions. So we're going to look here at log base a, and then we have an expression in the argument, and the u of x is a function. So more likely it's going to be like something that we've seen before. U of x could equal something like this, x squared minus 6, as in B, or u of x could equal a linear function, like in a up here at the top, example 9, 10 minus 2x. Alright, so let's see what the next page has in store for us. Example 10, consider the logarithmic function log base 5 of 3x equals 7. And here, u of x is 3x plus 7. And this is a linear function. It says find the domain and the vertical asymptotes. Okay, well, for a log function, what we do not want is for the argument to be less than 0. So what numbers make this expression greater than 0? Okay, well, we subtract 7 from both sides. We get 3x is greater than negative 7. We divide by 3. And then we get x is greater than negative 7 over 3. So, remember from above, we were given the standard form of a log function, and it stated that the domain was from 0 to infinity. Okay, but we don't just simply have x. This just means that we don't want the argument of the log to be less than 0, and that's exactly what we have written here. 3x plus 7 is not negative, it's greater than 0, and so this is the domain of this specific function, log base 5, with the argument 3x plus 7. If you wanted to write the domain of f in interval notation, we would just simply write, not negative infinity, but the domain would start at negative 7 over 3 and continue out to infinity. Alright, find the y-intercept. Let's see. To find the y-intercept of a function, we simply set x equal to 0. Now, if we were given log base 5x with no expression, okay, just an x inside the argument, then it wouldn't intercept the y-axis. Okay, the domain would be 0, so there would not be a y-intercept. However, the argument of this log is 3x plus 7, and the domain now starts at negative 7 over 3, so we will cross the y-axis, and we will have a y-intercept. To find it, we just simply set x equal to 0, or in other words, we calculate f of 0, which is log base 5, 3 times 0 plus 7 in the argument, log base 5, 3 times 0 is 0, and so we get log base 5 of 7. Probably going to be some odd number. I'll pull up my calculator to calculate it. And so we go to the home screen, and we need to go to math and log base, type in 5 for the base and 7 for the argument, and we get approximately 1.21. Okay, find the x-intercepts. For the x-intercept, we set y equal to 0. So f of x equals log base 5 3x plus 7, we would strike out the f of x, which is the same thing as y, and we replace it with a 0. Okay, and so now we have to solve this equation. Alright, we will translate this into an exponential form of this equation. The base 5 is the base of the exponent. Log equals the exponent, so we have 5 to the 0 equals the argument 3x plus 7. Well, 5 to the 0 is 1. And solving this equation would give us a negative 6 divided by 3, which is a negative 2. Okay, so the trick here was to convert a log form of an equation over to an exponent and realize that 5 or any other number raised to the 0 equals 1, and it turns into a really simple equation to solve for x. So our last exercise for this chapter, sketch the graph of the function. Is the function increasing or decreasing? Is the function 1 to 1? Well, let's see. The base, a, equals 5, and 5 is greater than 0. So that means that our log function is going to be increasing, and we don't even need to look at our graph to know that. If the base a is greater than 1, I should have put 1 here. 5 is greater than 1, then our function's increasing. If a had been less than 1 but greater than 0, then we would have written decreasing. Okay, so from above we were told that the y-intercept was 1.2. So we go up 1 and then a little past 1 for 1.2. The x-intercept was a negative 2. And then our vertical asymptote was at negative 7 divided by 3, which is approximately 2.6. Well, hold on, no. That would be 2.3. Negative 2.3. And so this is the location of our vertical asymptote. I think that has a P in there, but you get the idea. So as with any vertical asymptote, we draw a vertical dash line at 2 1/3. I'm going to claim that that is right there. So in other words, our log function does not want to cross this line, and it will not appear over here on the left because our domain is limited to x values that are greater than negative 7 over 3. So we've got 2 points in a vertical asymptote. This curve goes up through here and sort of flattens out, never becomes completely flat. And then from this point we want to pass through this last one and then break hard and turn downward and run alongside on the right of our vertical asymptote. So once you find a x and y intercept in the vertical asymptote, pretty easy to sketch the graph of the function. And again, this is f of x equals log base 5 of 3x plus 7. And so that completes section 3.3.